It's this. And if this thing here, called the determinant, was less than 0, you had an imaginary result, meaning if your parabola crossed the x-axis, you'd have a root here and a root here. If it didn't cross the axis, you'd have imaginary roots, because that's what the root of a polynomial is where it crosses the x-axis. It's where x equals 0. Or excuse me, where y equals 0 is the value of x. And is this thing useful for what we're about to study? Yeah, it is actually, because it works like this in our world now. We're going to use this imaginary axis, J, to represent reactants. This is just a bookkeeping system, just a way to graphically describe what's going on here, folks. Don't get too excited. But it is on the test. I mean, they're not going to show you diagrams quite like this, but the problems you may have to solve if you're going for a general and extra class test are going to go into this little realm. And this is R for real. This is imaginary. Because reactance is considered to be imaginary power. It doesn't really get dissipated. It gets stored and given back, but it has characteristics like power. It impedes the flow of current, and it has impedance measured in ohms. But characteristically, it's different because it's time variant. It stores rather than dissipates. The stuff on the R-axis is resistance, so that's real. That's real power. It turns into heat, and that's resistive. That's not X, that's R. And I had a diagram where I said impedance in general Z as X, which has two forms, X sub C, X sub L, and over here on this side you have R. There's your resistance, there's your capacitance, there's your inductance. All forms of impedance. All measured in ohms, all symbolized with the omega. It's just that this stuff and this stuff have these different characteristics. Time invariant, time variable, turns into power, stores and gives back. Now, when we put an axis together and we have a circuit that has one of these and one of these in it, what's the impedance? Well, it's a little bit of this, and it's a little bit of this. So it's somewhere out here, and oh, what do we do here? It could be a capacitor, it could be an inductor. Does it matter? Yeah. Convention time. If it's an inductor, X sub L, it's positive. If it is capacitance, by convention. No other reason. We just kind of arbitrarily said, let's do it this way, because if we don't do it this way, you're going to be inconsistent. So for consistency's sake, we have this axis that's imaginary, but in the positive direction it's the inductive reactance, in the negative direction it's the capacitive reactance. Remember that little circuit I drew way back when? It had one of these, a capacitor. It had a light bulb, which for all practical purposes is a resistor, and it had an inductor. It was my high school teacher's little demo. This thing is 60 hertz. It doesn't matter what the voltage is, but he varied the inductance until this guy and this guy were canceled out, and the bulb went to full brightness because the impedances caused by the inductor and the capacitor were negated. What he did is he had enough of this to counter this until it got you right back to there. That is what resonance is when you are down here and you've got your capacitor and your inductor equal and opposite in value, in ohms. So if I say somewhere, I probably erased it. I had something where I said, okay, we've got a circuit like this, and this thing was 100 ohms. And this thing's 100 ohms. And the 100 ohms in a capacitor depends on the frequency. But at the particular frequency, it happens to be that impedance. If the frequency goes up, the impedance goes down. If it's a capacitor, if the frequency goes up, the impedance goes up if it's an inductor. Another reason for making this thing on the positive end is it goes up with frequency. And what we have, if we have this and this, is a little bit of this, a little bit of that, and there's your impedance right there. Your value Z is some value of R, and I'm putting J in there just to say there's the imaginary part, some value of X. There'll be a number for R, there'll be a number for X. And that's your impedance. It's got two parts. It's got a real part, it's got an imaginary part. These things have a name in mathematics. They are called complex variables. Somewhere, if you were trying to think of what we're going to take for an elective in your 4th year of college just to fill up your distribution requirements, and then, let's see, maybe I need a math course. I don't want to take advanced calculus because regular calculus is bad enough. I don't want to take topology because only grad students really care to get involved with that screwy stuff. Oh, here's something called differential equations. By the way, that's a walk in the park course. That's one that's really easy, but don't tell my son that. He said, it's really hard stuff. No, it isn't. Everybody, at least the engineers that took it thought it was, a walk in the park. Then there's another one, sounds scary. It's called complex variables. Most people say complex. I don't like the sound of that word. It's easy stuff. It's really just how do you manipulate numbers that have two parts, a real and an imaginary part. And it's really kind of easy. Want to see a cute way to do it? There is your rectangular coordinate system. You got the vertical axis, which used to be called Y when you took algebra, and the horizontal axis, which used to be called the X axis when you took algebra. There's Y, there's X, and the arrow says it's positive going that way, it's positive going this way. And that's where your parabola sits over there. And there's another coordinate system that looks like this. It's a big circle. And both of them have this thing in the middle called the origin. And when I pick the value of X and pick the value of Y, or in this case the value of R and the value of X, and I said my impedance is right there, that's one way to locate it, is to say it's so much X and so much Y. And, in the case of the polynomial, it's Y is equal to, AX squared plus BX. And I won't even say plus C because it's on the origin. You could do the same thing here. It's some value of R and some value of J. Or you could say it is some value of radius and some angle, theta. The angle from the horizontal axis and the radius out to that point. If you're a boater, you call that range and bearing, using your radar station on your boat. Range is how far it is, and bearing is what direction, in degrees from the direction I'm traveling. Or if I'm not traveling, what direction on the compass is it? If it's 45 degrees, then it's halfway off the starboard bow. And the range is 3 miles. That's how far away it is. And that's, if you're looking at a radar screen, let's say you're a weather guy or tracking enemy aircraft or whatever, that's the way your radar screen reads. How far and what direction. Of course, it's three-dimensional nowadays because you have to have not just the angle this way, but the angle this way, but also you have the distance. And that's how you locate things in space. That's how you locate things in the universe even, is what angle from a plane called the horizon or another plane called the equator. How far up is the sun? That's called the declination. What angle rotating around the hour? That's called the, what is it called? It's called the hour angle, something or other hour angle. When you look for stars out in the universe, is a reference point called Aries. Everything else is an angle measured away from it called the sidereal hour angle. All those things fit into this measurement system. One measurement system is polar, and you keep track of two things. The magnitude and the angle. How many degrees and how far. In the other system, you have how much x and how much y. Both will give you the same value. The thing about this is you might want to switch from one to the other. The reason is if you are multiplying R1 JX1 times R2 plus JX2, you're going to have to multiply this times this and this times this and this times this and this times this and collect all the terms. Remember in algebra the expansions? No, you don't remember that, but there was one. Or you could do it this way. You got A at so many degrees and B at some other theta. Well, we'll call that theta, we'll call this one phi. But you know, two different angles, two different magnitudes. Multiply those together, you know what it is? A times B, theta plus phi. Add the angles, multiply the magnitudes. Wow, is that easy or what? When you have to solve a problem where you have parallel impedances, one of them is a capacitor, one of them might be a resistor. Remember the rule for parallel impedances? I'm going to use Z now. The product over the sum. Oh brother, I have to multiply these guys and they look like this? No thank you. Adding is easy. You just add the r's and the x's and you're done. So maybe if I change this into this for the multiplication and then change it back, life could get very simple. Yes, it can. And yes, that's what we used to do in college when we had to solve a problem like, what's the impedance of this thing if there's one of these and one of these in there? You switch to polar coordinates for the multiplication. And by the way, with division, if you're not multiplying but maybe dividing them, then it's going to be you subtract the angles and you divide the magnitudes. It's almost as easy. I had to do that with a slide rule. It was easy, but it was not that easy, but it was a lot easier than doing it with expanded terms and all that. Nowadays you have a calculator and it's got all the smarts in it for doing the conversion. You plug in x and y, you get out r and theta. You plug in r and theta, you get out x and y. It's nice to know what you should get, meaning if you are in this quadrant, you should have a positive angle. If you're in this quadrant, you should have a negative angle. And if you're in this quadrant, maybe a positive angle, but it'll be a negative magnitude. Now you gotta have a mental picture of what kind of result looks good. So if you get the problem wrong, if you convert from one to the other incorrectly, you're going to recognize it right away and not accept a bad number. As my teachers used to say, I can excuse sloppy arithmetic, but I can't excuse sloppy mathematics. You have to know how to solve a problem, even if you flip a sign somewhere. You make a mistake like that, I'll take a point or two off, but I will take a lot of points off if you absolutely get the logic wrong. And how do you convert from one to the other? I'll show you, but I won't go into too much explanation. There's your rectangular coordinate system, there's your polar coordinate system, which happens to have an angle and a magnitude. And this is an x and a y. I'm going to use the mathematical, not the electrical terms. This is r and theta. Y is our sine theta. X is our cosine theta. If you took trig, you'd understand why. Theta is the arctangent of y over x, and r is the square root of x squared plus y squared. Now, you can memorize those, you can remember those from your college days or high school days, or you can do something very simple. You can say, I'm going to see a question on the test, they're going to say, okay, we had a circuit that had a resistor and a capacitor. They're going to give you 4 answers. And what you know is, whatever the answer is, if it's got a resistor here and it's got a capacitor which has a negative value on the x-axis, it's going to be somewhere in this quadrant. If they give you an answer that has a, you know, they put it in polar coordinates, they'll say, okay, it's 37 minus 45 degrees. That could be one of the answers. The other answers will be other things, but you'll know this is the right one because it's the only one that has a negative angle. Remember, you measure angles going counterclockwise, maybe you don't remember. If it goes this way, it's negative. If it goes that way, it's positive. So you start at 0, you go to 90, you go to 180, you go to 270, and you do it by going to the left. The angle going counterclockwise is the positive direction. If it goes to the right, it's counterclockwise and it's negative. So only one of the only one with the right answer would be the one with the negative angle. Maybe only one of those 4 has it. Maybe 2 out of the 4 do. And you kind of have to say, well, you had 100 ohms of this and 100 ohms of this, and the square root of 100 squared, 100 squared, which is 20,000 each. You know, square root of that, you know, it's going to be something around that value. Only one of them is going to look like that value. By the way, what is the square root of 20,000? Sometimes you have to have your calculator with you to the test and say 20,000. Take the square root. Where's the key for that? Here it is. 141. I should have figured that out. 1.414, you know, square root of 2 kind of thing. So it could be 141 in a degree value like that. In other words, you don't have to solve the problem. You just have to inspect the answers and recognize logically where the right answer ought to be. That's the clue. All right, I had somewhere in this class to get into phase because questions on tests will be like that one, or they'll be more like this.